Okay, so in this video, we're going to be talking about the law of sines. And the law of sines is this basic idea that there is a common ratio between the length of a side and the angle that is opposite it as you go around the circle, as you go around a triangle. So larger angles are across from larger side lengths. So you can see this ratio expressed in a couple of different ways. Typically, you will have it expressed as sine of the angle over the length of the side in each of the three scenarios. So alpha here is opposite side A. Gamma is the third letter of the Greek alphabet, so it's opposite side C. Beta is opposite side B, and so forth. You can also see it sometimes expressed as reciprocals of these, so A over sine A. It doesn't matter. It's the ratio that's important. And as long as you're setting them up all in the same manner with signs on top or signs on the bottom, as long as you're consistent, then the ratio will work out. Now, so let's look at a particular example, and then actually two examples. One where we get only one solution. And one of the tricks about law of sines is that occasionally you can get more than one solution. So let's look at our example. So first example, suppose we have side A is equal to 5.8 and angle alpha is equal to 64 degrees. These problems are typically given in degrees rather than in radians. So be careful about the settings on your calculator. And then one other side, let's say side B is equal to 4.6, whatever the units are, let's say centimeters. Now, the important thing to apply the law of sines is that you must have one complete ratio. So you have to have a side and an opposite angle. It doesn't matter what the other thing is. You can have two angles, you can have two sides, but in order, you need three total things so that you have some two of these that you can pull out, one complete ratio, and then one where only one thing is missing. And so that's what we have here. So we have essentially this expression. We don't have the third one yet. We only need two of them. So what we call these doesn't really matter. I could call this extra side C, and it would just be, we would be using another part of this relationship. So if I replace these with the angles that I have, so 64 degrees, it's always a good idea to write in the degree symbol so that you remember that you have to think about it that way and change the settings on your calculator. And then also fill in 4.6. Now, what this means is that I can solve for sine B. So sine of 64 degrees times 4.6 divided by 5.8. 5.8 is equal to sine beta. And so I can actually evaluate my expression in my calculator. Again, make sure that your mode is set to degrees, or use the degree symbol in your calculator to let your calculator know that you are in degree mode. 5.8. And what I end up with is a sine of beta equal to 0.7128 ... And then I'm going to find beta by doing the inverse sine of my 0.7128 dot, dot, dot. Use all the decimal places your calculator gives you to get the most accurate answer. This is going to be 45.466 dot, dot, dot degrees, or approximately 45.5 degrees if we round to a single decimal place. Now, once I have two of the angles, I could easily find the third one. Recall the three angles in our triangle: alpha plus beta plus gamma have to add up to 180 degrees. So in this case, I have 64 degrees plus 45.5 degrees plus gamma is equal to 180, which means my third angle, 64 plus 45.5, is 109.5, and then that leaves me with 70.5 degrees. And now that I have this angle, now I can go back and I can use, I recommend using the values that were originally given in the problem. So not to use the 45.5 to calculate like the beta and B, because that's a calculated value. Use the ones that were originally given in the problem. You'll get a little bit better accuracy that way. You can also use additional decimal places, but sine gamma over C. And what we want to find now is side C. So if I rearrange this, I'm going to end up with C is equal to A sine gamma divided by sine alpha. Again, I multiply everything by C, and then I need to get C by itself, so I divide by sine alpha, and then I multiply by A, and so I get C by itself. And so now if I plug in these values, A was 5.8, and I'm doing sine of 70.5 degrees divided by sine of 64 degrees. And I'm going to get 5.8 times sine of 70.5 divided by sine of 64. And I get 6.0829 dot, 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 or again, rounding to 1/10 of a decimal place, 6.1 centimeters, if that's our units. So this is what you would do if you get one answer. Now, where the law of sines can sometimes lead you to more than one value is when the angle provided is small. So again, approximately less than like 45 degrees. But particularly if you're in the 30-degree range, when the angle is small, you are more likely to get two possible triangles. And so we have to kind of keep that in mind. The angle that you get for angle beta, you want to check to see if the first angle that you find, if an angle in the second quadrant which has the same sine value, would also give you another triangle. So we can try this on this problem and see if that happens. So what is the equivalent? So alternate beta would be 180 minus 45.5, which was the angle that we got before. So 180 plus 45.5 minus rather, because I want it in the second quadrant, would be 134.5. Now, here's the question. If I add the angle back that I had to start with, does alpha plus my alternate beta give me room for another angle in my triangle? So is the sum less than 180? Well, in this case, 64 plus 134.5 is 198.5. So this is already bigger than 180, and therefore is not going to give me room in the triangle for another angle. I can't have negative size angles. I'm already over the allotment. So this does not give me a second triangle. But when that initial angle is very small, not 64 degrees, as I said, typically like in the first half of the first quadrant, so small, 30 degrees is somewhat common. Then you do run into the possibility that when you solve for that angle beta, you get an angle that can also give you not only an acute version, but also an obtuse version. And then you end up with two triangles. So let's look at an example where that can happen. So example 2. So suppose you have side B is 43, side A is 22, and angle alpha is 34. Now again, we're going to take our ratios. Again, it can be helpful to like draw a picture of these, but don't let the picture sort of overwhelm the fact that you have to test the math, because the picture and the math don't always agree, especially when you don't know what the relative sizes are. But we have A and alpha, so side and opposite side, and we have another scenario. So another side that we can work with. So let's plug these in and see what we get. So sine of 34 degrees divided by 22 is going to be equal to sine beta divided by 43. And if I rearrange that, so what do we get when we plug this into the handy calculator? 43 sine 34 divided by 22, we get 1.09. And so this is another scenario that you also kind of have to watch out for. sine values cannot be greater than 1, so no beta exists. So this is not possible. So let's try, so what this is saying is that the largest, the angle that you need is actually too big. There's no, the side is too short. So let's try, we need to divide by a longer side. So let's make our side a little longer and try again. So let's make this 27. And then we're just changing the length of the side to try to make it long enough so that our triangle actually closes. So let's see, again, the math is all the same, but let's see what happens when we replace 22 with 27. Now we get sine is 0.890566. And the value of beta in the first quadrant is going to be 62.9445 ... or approximately 62.9 degrees. Now, that's the obvious one. What about alternative beta? So second quadrant beta. Well, remember it's 180 minus the value we got in the first quadrant. Which is 117.1. Oops. Now, let's think about this. We know that 62 and 34 are definitely going to be less than 180. 62.9 plus 34 is going to be 96. So in triangle 1, gamma is going to be 96.9. Sorry, it's 180 minus that. 83.1. And in triangle 2, gamma is going to be 117.1 plus 34, and then subtract that from 180 is going to be 28.9. So there are two triangles because I can let beta be this, and then this will be the second longest side, and the side across from gamma will be the longest side. But I can come up with a triangle where beta is the biggest angle and B is the longest side. And then there is enough room to make another acute angle inside my 180-degree total, where C is now not the longest side, it's actually the second longest side. Now, for both of these, we would have to then find the side length that is appropriate, that is consistent with that side length. So let's calculate the rest of triangle 1. So remember, it's sine alpha over A is equal to sine gamma over C. and we know we want to solve for C. So we rearrange this before. You multiply both sides by C to get C by itself, and then you divide sine gamma by sine alpha, and then multiply by A. So in this particular case, we would get sine gamma in the first triangle is 83.1 times A, our original A was 27, and then divide by sine of our original alpha, which was 34. And then we throw that into our calculator. Sine 83.1 times 27 divided by sine of 34, and we get 47.934 ... or approximately 47.9. And then we do exactly the same thing, but now for angle, the second triangle, where our angle is not, in fact, 83.1, it's 28.9. Everything else remains the same. And we end up with, again, a shorter side. In this case, it's the smallest angle in the triangle, and therefore the shortest side, 23.3347 ... or 23.3 units long. So the in one triangle, the obtuse angle, or the largest, not actually obtuse, but still in the first quadrant angle, is angle gamma, or across from side C. But in the second triangle, beta is the largest angle. And so it also, therefore, the 43 that we had at the beginning for the length of that side is also the longest side. So the law of sines can be a little tricky because you do have to remember to look for that second angle, and you can sometimes get problems where there is no side that closes the angle, where the angles are just, the sides are too short or the angles are too large in order to accommodate that. But that second triangle is most often going to show up when the initial angle that you're starting with is particularly small. But if you're given two of the angles, generally it's easy to find the third angle. You know the triangle is going to exist. You just have to find the lengths of the sides. But when you're given two sides and an angle, you can end up with these scenarios where there's only one triangle, where there's no triangle, or where there's actually two triangles that satisfy this requirement.